In AP Physics C, we will go into a little bit more depth about how I'm talking about what I'm about to talk about, which is already all babbledy gooped. Here, I'm just going to kind of come at it and just kind of show it to you and say, this is how we're going to use it. This is how we're going to use it. So we already have, right, our linear equations for force, momentum, work, kinetic energy. Actually, what are some other force? I'm going to wedge in here inertia, because now that position matters, the term for this, where you say position matters, or what are known as moments. So you can have, right, a moment of force, a moment of momentum, a moment. You wouldn't necessarily call them moments of working kinetic energy, but you would have moments of inertia. And so all that word moment means is position and location matter. When you were in Physics C, you'll be asked to calculate these. In Physics 1, you just need to be familiar with them. So we're just going to kind of give you the one pass and then take a look at it. So moment of inertia is related to how much mass you have. Let me come back to this in a second. The moment, your inertia, right, is your resistance to move, is really accelerate. And so when we talked about force, that's F equals ma. But when we get over here to rotation, I want the moment of force. So the moment of force becomes my position, right, position matter now, times that force. And it's very much, we use the cross product. That turns into R cross F, which is RF sine theta. If that theta is 90 degrees. Right? So this is what the lecture was about. That's how we kind of got ourselves to torque. Right? That's why we call this. This is that torque. That's R cross F. F is MA, but over here I'm rotating. So A is R alpha. So what you end up with is R times F, which is MA, but I'm rotating RM, R alpha, and I end up with this MR squared alpha. This becomes my resistance to rotate, to accelerate rotatingly. So it becomes my new, this mass and position is my moment of inertia. Here is my moment of force, that's torque. I now have this moment of inertia, which was related to how much mass you have and its position squared. There is a constant that's in the front of here that will change based on the shape of the object, on how the mass is distributed through, just like we did on the bat. If you've ever swung a bat, flip it around and swing it the other way. It's easier to rotate. So it depends both on how much mass and where that mass is located and how it's distributed to. And so we break it up into tiny little chunks, and then you sum up the little chunks. And when you sum up little chunks, that's known as the integral. So we won't talk a whole lot about it. But if you have, right, there's a whole list, right, of a list of moments of inertia that is called capital I in the book. Could you calculate them? Yes. Will you be asked to? No. So this becomes my moment of inertia times alpha. What about momentum? That is my moment of momentum. Nobody says that, but that's really what it is. R cross the momentum, R mv sine theta. And again, we make theta 90 degrees. That turns into 1. R mv. V is R omega. R m R omega. Oh, look, there's that mr squared again, and omega I omega. And because we want to talk about, just like we changed the value for, we changed the word that we're using for torque from F to T. This stops being P, and this turns into capital L. Why capital L? Literally because momentum just gets all the leftover letters. So this turns into I omega. That's a vector because omega is a vector. Same thing over here. Torque is a vector because alpha is a torque. I'm sorry, alpha is a vector. There's that moment of inertia again. All right. However, when we get down to here, where we can't use the cross product because these aren't vectors. So we just kind of using this idea that whenever if we can get ourselves to an mr squared, we can figure out, just kind of plug some stuff in. Work is force times distance. It just turns into torque times delta theta. You won't be asked to do rotational work. And then kinetic energy, this is 1/2 mv squared. But my thing is rotating. That turns into 1/2 m. V is r omega squared, which then turns into 1/2 m r squared omega squared. There is that I again. 1/2 I omega squared is rotational kinetic energy. Now I can have energy based on how I am spinning, how I am translating, or when we get in the terms of talking about an object rolling, it's doing both. This is really all that you need to get through. We don't talk about rotational work, by the way. Unless in terms of changing the kinetic energy. Yep. Yeah. Nice. So, there. L equals I omega. That's an L. Torque is I alpha. And then you have your moments of inertia inside of there.